So, welcome everybody to the AJS seminar of today. So today we have with us Francesco Nobili, who is a last year PhD student under the supervision of Professor Nicola Gilli, and he will talk about a differential perspective on gradient flow on cut-zero spaces and applications.
Thanks, Manuele. Thanks, Maria, for organizing this special session. So today is a joint work joint with Nicola Gilli, my advisor at CISA. And I will speak about gradient flows on cut-zero settings, which are metric generalization of manifold with non-positive curvature. And we will make a bridge with differential perspective together with an application of geometric analysis. Okay, so the talk is split into parts. As I just said, we will face the metric theory of gradient flows on this special class of metric spaces, and then link the first order geometry of such spaces with the gradient flow notion by appealing to a special subdifferential formulation. In the second part, we will face an application of these results for the harmonic map problem, which is a fundamental problem in differential and Riemannian geometry, which faced several Nonsmooth generalization in the past year and became a hot topic. So after a brief introduction, we see how to adapt the first part of the talk in order to get a notion of a harmonic map heat flow at this Nonsmooth generalized level, and then derive a notion of tentative notion of Laplacian. So the motivation to study not metric gradient flows in the space of metric measure structure or probability measures is because it's a powerful tool to make analysis. And from in the class of spaces that we are going to see, so this synthetic generalization of Riemannian manifold with synthetic zero upper bound on the sectional curvature, a metric notion of gradient flows was already faced in the 98 by Meyer. And only later in 2005, its link with the differential point of view of cut-zero spaces, so this class of spaces, was investigated by Lichak. So we are motivated by the study, as I just said, of harmonic maps with no smooth source and target. This is a program that was initiated by G and collaborators, which aims at showing some Lipschitz regularity of harmonic maps. But our goal would be to derive a notion of differential notion of gradient flow of the energy of a map together with a notion of Laplacian. So to start with, I will give you the definition of these cut-zero spaces, which are metric spaces, complete, and geodesics, meaning that you can join arbitrary points of the space with a geodesic. It is always intended to be minimizing with respect to the endpoint, constant speed, and parameterized on 0, 1. And I require to this metric space to satisfy a semi-convex inequality of the distance square to any point of the space. So I'm requiring this semi-convex inequality, which turns out that implies that the geodesics are unique with respect to endpoints. I will denote these geodesics by this notation. So the gradient flow on this space, in general, gradient flow is a curve associated to a functional E on the space, which starts at a point y0. And I want to make a meaning on this class of spaces of this differential inclusion, which is the thing that you would require on a smooth space, like for instance RD. And this is the equivalent. For instance, if E is the Dirichlet energy, this should be the heat flow. So to start, let's investigate a bit the first order geometry of these cut-zero spaces. So at each point of the space, you can attach a metric cone called tangent cone, which roughly is a tangent space consisting of directions of the space. And the metric dy is just, for instance, if you think of direction as a geodesic that emanates from the base point for a positive time, then you think it as a direction on the tangent cone. And the distance here is basically evaluating how infinitesimally how geodesics fall apart one of each other. And then if you complete this structure of directions in a suitable way, you can always find something else, like for instance, right speeds along absolutely continuous curve. And another property that is really important for us is that in somehow the tangent structure inherits the curvature upper bound of the base space. So if you start from a cut-zero space and you pick a tangent cone, then this turns out that is again cut-zero, and also has some kind of positive homogeneity, meaning that you can multiply, for instance, directions with positive scalars. You can then formally define a kind of a sum on a tangent space by just formally define a sum as twice the midpoint between two vectors. So recall that tangent cone is cut-zero, so is a geodesic space. So between two vectors, you can actually link the two directions with a geodesics of direction. And this is nothing but the parallelogram. While the third fact is that you can define, again, an inner product which resembles the scalar product that you have on a smooth space by just imposing the polarization. And you can convince that this inner product satisfies all the usual calculus rule, not relying on linearity. That's because you cannot multiply, for instance, a vector with a negative value, -1, for instance. This is because there is no really a notion of negative direction on a tangent cone. While you can, even if you cannot say that this inner product is linear, it actually turns out to be concave. And with respect to these formal sums we defined. And also the cone tip would be this OY, this notation, the zero. So in the literature, it's well known that this class of spaces has a number of similarities with the Hilbert spaces. For instance, I recommend the book by Bakak. And what I will need is a notion of metric projection onto closed and geodesically convex subset of the space. So you can always project. And there is also a notion of a sequential convergence, weak convergence for bounded sequences. So the first definition in order to discuss gradient flow is the notion of minus subdifferential, and keep a second for I will define why this is minus subdifferential. So in general, for a convex and semi-continuous functional, the minus differential of the functional at a point y is the collection of direction, tangent direction, for which this subdifferential inequality is in place. And I denote the domain of the subdifferential just the collection of base point for which it is not empty. So there is no really a direct correlation between minus subdifferential and the straightforward definition of plus subdifferential. So you cannot bring this minus inside, for instance, because there are no negative directions. And since I'm interested in the minus subdifferential for the very definition of gradient flow that we will have, I will stick to this definition with the minus. And I observed that when it is not empty, this set is closed and convex. This is because inner product is concave, so with the minus is convex. Therefore, you can always project the contip onto the subdifferential set. And also there is a kind of property of the space for which this too implies weak sequential convergence, closures, sorry. So my definition of gradient flow on this class of spaces, on K0 spaces, for a convex and semi-continuous functional, gradient flow associated with the functional starting from a point y0 in the closure of its domain is a locally absolutely continuous curve with values in the K0 space, for which the subdifferential inclusion almost every time holds true. So recall that I defined all the objects here. So there are right speeds of absolutely continuous curve. I just defined the minus subdifferential set. And the line of research here is understanding whether or not this definition is non-empty. So in some way, we need to understand how it's linked to previously known notion. And the first one who noticed that K0 spaces are suitable framework in order to investigate gradient flows is Meyer, where he proposed the notion and proved the notion of gradient flows in the evolution variational AVI inequality sense, the AVI condition. So I will spend just one slide to speak about how you should build this gradient flow in the AVI sense. And I will start from the smooth situation. So in RD, the gradient flow is nothing but an ordinary differential equation where the curve is basically pointing at each time in the steepest descent direction of the functional E. So how you would build such curve? Just you ask for some help to the numerics, and you freeze a time step tau, and then you perform a for loop with an implicit Euler scheme in order to find a collection of points satisfying a discrete version of the ODE. So if you pay attention of line 3, this equality is nothing but the Euler-Lagrange equation associated to this Moroi-Yosida energy functional. And this is a well-posed minimization problem on K0 spaces because we have the convexity of the distance squared. So you can always take this minimum, and you can perform in this sense the implicit Euler scheme, also called minimizing movements. So you can therefore build up a discrete solution with parameter tau, which is a piecewise constant interpolation of these points. And by just writing down the convexity of this function, you basically end up with a discrete version of the AVI. So the goal here is just to prove Cauchy estimates in tau in order to exploit the completeness of the space of continuous path and bring the AVI condition from the discrete level to a continuous level. So the link of my definition of gradient flows to the previously known, in the sense of AVI, is just basically a remark, and which thanks to which we can link the metric notion to the differential notion. So if you have an absolutely continuous curve with values on K0, it was noticed that you can always find the right incremental ratio, but also that you can link the variation of the distance squared with the inner product on the tangent cone along the curve. And this can be done at almost every time. So it's just a corollary to notice that either you have the evolution variation inequality, or this is an if and only if you have the subdifferential inclusion at almost every time t. So it's really my definition really is equivalent to the VI in this sense. What is not was not known, and what is the second goal of this part is to understand in which sense the flow is regularizing. So if you consider a gradient flow in a Hilbert space, it's well known that the gradient flow selects the element of minimal norm among all the vectors in the subdifferential. And this is kind of regularization property, because actually the flow grants that the subdifferential is not empty, because at every time t you can prove the strong convergence of right incremental ratio to the element of minimal norm. So being in the domain of the subdifferential is some kind of regular property. And what we noticed by basically exploiting the first order differential geometry of Cat0 spaces, and also the notion of weak convergence, is that in this sense, when you look at the right incremental ratio that on a Cat0 spaces is this direction, it strongly converges in the tangent cone to the element of the minimal norm at every time t. And so actually also at time equal to 0, provided the starting point was regular enough. With this part, I finished this part and I move to the second part of the presentation. So I will start by introducing the problem of harmonic map, and then we will see how it's linked to the notion of gradient flows I just derived. So in differential geometry, a smooth map between the Riemannian manifold is harmonic and defined on a domain omega with the prescribed Dirichlet boundary values, provided it's a critical point of this total energy functional. So the examples that you may have encountered so far are the notion of harmonic functions, which is the trivial scalar case of a harmonic map with target R, but also the geodesic, because if you think of geodesics as a minimizer of the length functional, then the length functional is just this energy functional when you have a one-dimensional source. So the well-posedness of this theory and the regularity were identified in the seminal paper by L. Sampson in '64 under the key geometric requirement that U is a smooth map Cat0 valued. So here I mean Riemannian manifold which is also Cat0. This means that is non-positively curved in the sectional curvature sense, and with some rich lower bounds on the source space in order to make geometric analysis. And I will spend one slide to convince you that the Cat0 constraint in the target is a natural property that you should ask for the well-posedness of this theory. So existence and uniqueness can either be obtained via direct method or via the gradient flow if you see it as a minimizing sequence for the total energy functional. And this is because the functional, so this functional E, turns out that it's strictly convex thanks to the assumption on the target. And you can see this because the Hilbert-Schmidt norm over here has hidden the matrix tensor of the target. And the minimizer are also stable in the sense that if you perform a second variation of the energy around an harmonic map, then the sectional curvature tensor pops out, and if you want to get rid of it, you need the assumption of non-positive curvature. Also, they noticed, L. Sampson, they proved this, famous general Bochner formula, which in this setting reduced by getting rid of the Ricci tensor and the sectional tensor of the target with this easier inequality, which actually improved the regularity of harmonic map by elliptic regularity arguments. So I didn't say exactly what in here, how it is convex. We will face this convexity along geodesics interpolation of mass in the sequel. So what actually is well established in the literature is that this theory of harmonic map extend to Nonsmooth setting, and this became a hot topic after the 90s. The first references that I will mention are Gromov-Schoen, which in the 92, they faced the harmonic maps from a smooth source to a metric target, which was a Riemannian polyhedra of non-positive curvature. But in the 93, together with Koival, there was a full Sobolev theory, and then the definition of a harmonic map was given with a cat-zero general target. So they were able to propose a Sobolev theory made of directional and total energies, and a notion of harmonic maps as minimizers of total energy functional. And of course, they were concerned about proving the local Lipschitz regularity of minimizer, which they did. If you want to make a further step, then you need to make all the source singular, and you end up in the reign of metric measure spaces, which are Polish spaces equipped with boundedly finite measure. And I will mention that in this case, there are results of Yost, where who proposed a notion of generalized Dirichlet form, where harmonic maps are minimizers. And among the property of, among the requirements of cat-zero target and singular source with some Poincaré and doublet condition, he obtained Holder regularity. While in the breakthrough paper of Zhang Zhu, a harmonic map between an Alexandrov space and a cat-zero target were discussed, and the local Lipschitz regularity here finally was achieved. So for my presentation, I will be focusing on these two references. So at the end, G, with his former postdoc, Tunelev, started from the theory of Koival-Schoen and discussed harmonic maps from an RCD-KN source to a cat-zero target. I will spend some words in the next slide about RCD-KN condition. But the point is that in this fully singular set, they were able to achieve again a satisfactory Sobolev theory made of directional and total energies, and discussed the minimizer with prescribed boundary Dirichlet condition. So the setting should be RCD-KN source, but for the purpose of this presentation, actually I will only need a first order differential structure of the spaces. RCD-KN spaces are a generalization of a Riemannian manifold with the Ricci curvature bounded from below by a number k and an upper bound n of the dimension. As I said, I will just need the first order differential structure, which if I wrap up some of the recent literature, I can say that they have the property of to be strongly rectifiable, in the sense that for every epsilon, you can find an epsilon atlas, which is made of a countable number of charts and charts domain, where charts domains are compact subset of the space, and they partition the space up to a negligible set, while the charts are just the mapping portion of the space to Rd, and they are 1 plus epsilon B Lipschitz. A crucial property that these charts satisfies is that when they map, they push the reference measure on these portions, then they are absolutely continuous with respect to the Lebesgue measure. And here the apex d is an integer which is less or equal than n, and it's also called in the RCD setting essential dimension of the space. So from now on, I will assume always an RCD-Kn condition, omega an open subset with finite volume, and the target space is a separable K0. But for the purpose of your understanding, maybe, you can also think about a manifold as a source with rich lower bounds. And this strong rectifiability is actually the notion of an atlas. If you think that you can shrink with this epsilon parameter in order to have charts which are really 1 plus epsilon by Lipschitz. So the first tool we need to introduce is the notion of the energy at this level of generality. So you take an L2 map, and you see that it is in the Convex space, provided this number EU, which represents the energy, is finite. So this double integral of this difference quotient squared is finite when you take the radius going to 0. And the first things to discuss is in how this inner integral speaks to differential structure of the space X, because the energy functional was in the smooth category just the integral of the Hilbert-Schmidt norm squared of the differential of U. So in order to do this, I will start with the easy situation of a Lipschitz function, a Lipschitz map from Rd to a metric space complete. And there exists, due to Kirchheim, a metric Rademacher theorem, which basically states that at almost every x, you can find a semi-norm called the metric differential of the map U at x, which approximate at first order the map, meaning that the limit at the point goes to x inside the subset P of the distance minus this metric differential in x minus tilde over x minus x goes to 0. So the delicate part here is how to bring this differentiability to the RCD-Kn space. And so how to build a metric differential which is global but local for a map which is Convex space. And the idea is that if U is in this Sobolev space, Convex is also using Lipschitz. And since the charts domain are compact, then when you see the map U through a chart, then it is Lipschitz, and you can apply the first point. So you end up with, for every portion, a metric differential which depends on this epsilon. And the delicate part here is how to make a patchwork of this differential in order to have a global object on the space X. And in order to do so, you need to carefully take this epsilon down to 0. With this procedure, you can also prove that the inner integrable, so this average here, is actually a limit that converges in L1 to this energy density of a map U. I call it energy density because it's the language used in the conversion paper. But through this limit, you can see that finally there is a link between the energy, the tentative notion of energy of a map, and the differential structure of the space. At the end, so you recover actually a notion of energy of a map U, and the notion of energy density, which is the counterpart of, in some sense, of the modulus of the differential of U squared. So I also mentioned that in order to get this limit, it's crucial to have this good behavior of the reference measure under the charts, because from here you need to go to the Lebesgue measure. So you need to use this condition before. Also, the cat0 up to now property was not used, but it's really helpful when you want to discuss convexity property of this functional, of this energy. So if you repeat this construction for maps defined on open sets, you can actually, with just technical difficulties, derive a notion of a map, which is conversion from an open set and has this finite energy. And whenever Y is cat0, so the target space is cat0, then it's essential to understand what is a geodesic of the space of L2 map. It exists because you can actually interpolate between geodesics of this. You can interpolate the images of two different maps via geodesics of the target space. And thanks to the very definition of the L2 metric of maps, you see that this assignment is a geodesic with values here. And since at almost every point, the distance square satisfies the semi-convexity, then also this distance squared of L2 map satisfies the good semi-convexity properties. And so in other sense, we are saying that if Y is cat0, the space of L2 maps is cat0. And the energy function that associates to an L2 map, its energy, if it's in the Sobolev space, plus infinity otherwise, is strictly convex and semi-continuous. So we finally reached a definition of harmonic map with boundary values U bar as a minimizer of the total energy functional subjected to the constraint that U has the same values of U bar at the boundary, which in this metric framework can be written as this. So the distance between the two maps is Sobolev with the homogeneous Dirichlet condition, boundary condition. So if you apply finally the first part of the presentation to this functional, which is defined on a cat0 space, you end up with a Nonsmooth notion of a harmonic map heat flow, which is associated with the energy functional. So I remark that up to now, I can just say that the minus subdifferential of this energy functional is in a tangent cone along the curve of maps. So it's essential to understand this object. So what is is an object that is now it's defined because L2 is a collection of map, as a set is a cat0 space. So you can have tangent cones on a cat0 space, but it seems very abstract as a definition. In fact, if you look at the smooth category, an harmonic map between two Riemannian manifold, then the Laplacian is a smooth section of the pullback tangent bundle, and you can convince yourself about this by just taking Rn and Rm So Laplacian is a vector which, if you pay attention on not identifying the tangent space with the Euclidean space itself, lives on the image of U. And the minus subdifferential should be the Laplacian, because you know that heat flow is something of this form. So in some sense, if you attempt to define the notion of Laplacian as the element of minimal norm of this minus subdifferential, you end up with a definition of Laplacian which is way too abstract, because it's in this abstract tangent cone, and which totally miss the link with the differential structure of Y. So we are expecting some kind of section of the tangent space on target. So the next step is to understand and make rigorous this link. And by starting with the definition of a geometric tangent bundle of a Cat-zero space. So in general is a geometric object which can be equipped with a sigma field that communicates with the metric structure of the fibers. And a Borel section of this bundle would be just a measurable assignment y as y inside of it, such that as y belongs to the tangent cone at y. So while on the other hand, typical elements of the tangent cone attached to an L2 map, as we said, are obtained as velocities. So from geodesics of the space of L2 that emanates from U for a positive time. And if you look a bit about this, what's happening on the target space, you should realize that any vector here is a kind of infinitesimal variation around the map U, because we said that these kind of directions are obtained as a collection of directions of the tangent cones of Y for M almost through X. So what you need really is a notion of pullback geometric tangent bundle. So the key remark is that if you have a section of the geometric tangent bundle at Y, which is U push forward M almost everywhere defined, then with true integrability, then when you see through the map U, so you pre-compose with U, you have an almost everywhere defined object which has the same integrability. So the natural definition of geometric pullback geometric tangent bundle is the following, and as in the Y case, you can equip it with a sigma field. And the picture here is that you take all the bundle, and in some sense you make which lives on the image of U, and you bring it back a copy of it on the source space. And when you ask true integrability of the section of this object, you end up with a notion of L2 integrable section, which are Borel assignment with finite L2 norm, which are identified almost everywhere. So if you push the definition from the simpler object, so the direction on L2 maps, tangent direction of a L2 map U, to the what is expected to the pullback section, and you push this definition to a simpler and best class, you actually end up with a bijective isometry between these two actually metric cone. And this is the good framework in order to define finally a Laplacian. So the domain of the Laplacian is a subset of the correlation space, and is, as a set, the domain of the subdifferential. And for every u of in this domain of Laplacian, the Laplacian is just the identification through this map of the element of minimal norm. And this is a good notion because it satisfies first variation formula. So for every v, if you consider the geodesics interpolation between u and v, then the subdifferential inequality is when you define the Laplacian to be the element of minimal norm, can be reduced to this first variation. So if you think about, for instance, harmonic functions, you should expect here an equality, not less or equal. But this is not really possible at this point because the geometry of the target space is kind of an obstacle. So the tangent cones are not really tangent space, so you cannot take negative directions, and you cannot perform, in this sense, a two-sided variation of the energy. Therefore, you just have an inequality. And thanks to this fact, you can finally recover that a map U is harmonic if and if it's in the domain of the Laplacian with zero Laplacian, meaning that it's the trivial pullback section. To conclude, just say that there are simplifications which can be removed. For instance, separability of the target, and also you can actually get the full bridge with the differential calculus on RCD spaces and link the total energy. So if you appeal to the notion of differential of a map U, and you believe that there is some kind of Hilbertianity at small scales, then you can link the energy density we achieved with the metric differential alla Kirchheim with a true differential, and it's a Hilbert-Schmidt norm. With this, I thank you all, and I conclude.
Thank you, Francesco, a lot for your seminar. Now it's the moment for questions. If somebody wants to do a question, he can mute himself and ask a question. Or write in the chat, maybe.
Hi, can I ask a question?
Yeah.
Okay, first, can we come to page 16? Page 16, yeah. There's two limits where you are taking, like at the top, you are taking the limit sup as r decreases to 0, and at the third item, it directly takes the limit.
Okay.
Is there a reason, or can you always exchange the order of limits?
No. It's no. In here, actually, here there is also a limit of epsilon goes to 0, but so it's just delicate. You need to make this patchwork of metric differential. But here I'm not super sure if it should be no. It's a lim sup. Here is a lim sup. The point one is okay. Here you need to prove that the limit exists.
I would be fine, but from the third item you directly wrote the limit.
Yeah, because indeed you need to prove that the limit exists at the end. Because as you see, here you want basically L1 convergence of this object in order to have this representation.
So in the end, you change the order of the limit and the integration, right?
It just so if you start by proving the M almost convergence, yeah, and then you improve it to L1 convergence by dominated convergence argument.
Okay.
But here there is no integral, so this is something deep that you must prove.
In the fourth item.
Yeah, no, here it's something that you need to prove.
Okay.
It's not coming automatically out of this.
Okay.
It's exploiting all the charts domain of the RCD space, and the chart properties.
Okay. Then I still have another question, like coming several slides later, which I forget. I mean, later, what is the regularity assumption on X? Is X also a metric measure space, or X is a smooth space? Because sometimes you used like a W12 on omega.
This one?
Yes, yes.
Okay.
What is the regularity of on omega?
Now, omega up to now is just an open set of X.
X is,
for simplicity, X is this generalization, is RCD spaces, so a generalization of Riemannian manifold. But at this, like in order to introduce this Sobolev space, of course, there is a metric notion. Omega is just a subset, open subset.
Okay, so my question is, does the X is also a singular space like RCD, right?
Yeah.
Okay.
In this slide, yeah.
Okay. A final. I mean, do you have also the tension field for the harmonic maps?
Exactly. So in the smooth situation, this Laplacian is called tension field, and and the heat harmonic map flow would be actually here with a tension field. So we just decided to call it Laplacian.
Okay.
But it's really the same object.
Okay.
And the tension field is the one you would get here with an inequality. So if you think this as the Riemannian metric, here there is some pullback tangent vector. Here there is the tension field.
So this Laplacian U is actually how to say quadratic in U.
So this is really a calculation in the Riemannian geometry, while we recover it through the gradient flow. So for instance, you can find in the Yost book about geometric analysis.
Okay, sure.
So you can really perform this variation and compute, and you end up with a tension field here.
No, my question is like the Riemannian tension field is actually a quadratic form in U, right? In gradient U. It's
yes,
like,
and you would have it on the right hand side. So I don't have the smoothness to compute this limit, but if you perform this limit on a Riemannian manifold, you would get exactly a pairing between grad U and some covariant derivative of this direction.
Yeah.
So in this sense, yeah, it's a form.
Yeah. Okay. Yeah, it's just like Laplacian U makes me feel like Laplacian U is linear in U, but actually it's not. Okay, thanks.
Welcome. Of course, it's linear if Y is just the Euclidean space.
Okay, Francesco. Yeah, Francesco, I have a question on. So usually when I imagine the Laplacian to be the only element in the subdifferential of the Dirichlet energy to several contexts. But in this case, it's not clear to me if the Laplacian of U and the minus subdifferential the Laplacian belong to the space on which we define the minus subdifferential. So
no, you can see that like over here. So you can say, so mine is a definition, of course. Then it's up to maybe future research to convince everyone that is a good definition. But so I'm defining the Laplacian to be the element of minimal norm in subdifferential. But if you look at the Riemannian case, so you need to have some link with the differential structure of the target. So we just decided to make this link via this identification, and then define the Laplacian as the identification of the element of minimal norm.
Ah, okay, okay, thanks. Ah, okay. What was this map?
It was this map over here that, so the subdifferential as a set of the energy is something that lives in here, because the energy functional takes an L2 map. So subdifferential is something that lives naturally in the tangent cone of a map. While we want to have a Laplacian which lives, which is a pullback section of the geometric tangent bundle, of course with these two integrability. So you just map the element of minimal norm in this space. That's what we have done.
Okay, thanks. Okay. Okay, I see that there are no further questions, so I propose to thank Francesco again, and we meet as always on next Friday.
Thank you.